Hello everyone and welcome. People often say that the race in power battery technology has two stages. The first is an arms race in battery chemistry. The second is a battle of manufacturing precision and testing validation. Today, instead of talking about what's happening inside the battery cell, we're focusing on one of the most demanding stages. Before a battery leaves the factory, environmental testing under extreme temperatures. Here's a practical question. Can a battery really be fast charged inside a chamber operating at -40 degrees Celsius? And more importantly, how can an environmental chamber communicate seamlessly with a battery charge-discharge cycler? To answer these questions, we're joined today by Mr. Wang, Senior Testing Expert at Tomilo. Welcome, Mr. Wang.
Thank you. It's a pleasure to be here. Today, environmental control has become an essential part of laboratory construction. For both battery manufacturers and automotive OEMs, if you look at the entire battery manufacturing process, environmental control is essential every step of the way.
How so?
Let me give you an example. During battery formation and aging cells undergo their very first charge-discharge cycles inside a sealed chamber maintained at 45 degrees Celsius. Now imagine the chamber isn't perfectly uniform. One side is at 45 degrees Celsius, while the other is only 43 degrees Celsius. That small temperature difference causes the cell layer to form differently from one cell to another. The result is that cells within the same battery pack begin to age at different rates. Some degrade prematurely while others remain unusually active. For the battery management system, that's a serious challenge. In many cases, manufacturing yield is gradually lost because of poor temperature and humidity control.
That brings us to one of the industry's biggest challenges. Many companies invest in premium environmental chambers and high-end battery cyclers. Yet once the two systems are connected, synchronization often becomes a problem, whether it's temperature cycling or ultra-fast charging under extreme cold. Why is this so difficult?
The key issue is synchronization. In many laboratories, the current workflow looks like this. First, the chamber cools to the target temperature, for example, -20 degrees Celsius. After holding that temperature for 2 hours, an engineer manually confirms that the chamber is stable. Only then is the battery cycler started. That gap between environmental control and electrical testing creates a disconnect.
It sounds like an inconvenience more than anything else. Does it really affect the test results?
For routine testing, perhaps not. But for compliance with standards such as GB or T38031, or more demanding internal specifications, it's a different story. Take low-temperature fast charging tests as an example. In real life, a battery may sit overnight at -10 degrees Celsius. The moment the driver starts the vehicle, a high current is applied immediately, even though the battery core is still extremely cold. With the conventional approach, the battery is first held at the target temperature before charging begins. By then, the entire cell has cooled uniformly, making the test conditions much more predictable and the associated risks relatively manageable. True synchronized testing is different. The environmental chamber continuously cools at a controlled rate such as 1 degree Celsius per minute. The instant the target temperature is reached, the battery cycler applies the programmed high-rate charging current. Only this dynamic interaction can recreate the most critical lithium plating conditions seen in actual vehicle operation.
That sounds incredibly demanding. The environmental chamber relies on pid temperature control, while the cycler responds within milliseconds. So how do these two systems communicate? Surely they don't rely on manual coordination.
Of course not. The answer is integrated control software.
So how is this achieved in practice?
Typically, you'll need either a third-party control platform or an advanced battery cycler equipped with an integrated environmental chamber control module. First, both systems need to communicate using open protocols such as CAN RS485 or Ethernet. More importantly, the battery cycler should use the chamber's real-time temperature feedback as its trigger, not simply a preset timer. Second, synchronization logic is essential. While the chamber is heating or cooling, the cycler remains in standby. As soon as the chamber confirms that the target temperature has been reached and stabilized, the cycler starts automatically.
Ideally, that response delay should be less than 1 second. What happens if the chamber can't cool fast enough or if the temperature overshoots? Wouldn't that compromise the test?
That's why equipment selection is so important. When choosing an environmental chamber, don't focus only on whether it can reach -40 degrees Celsius. Pay close attention to temperature overshoot. Although the national standard allows ±3 degrees Celsius synchronized battery testing, typically requires overshoot within plus or minus 1 degree Celsius. The second consideration is cooling capacity under load. During charging and discharging, batteries generate their own heat. For example, a 1C discharge may increase cell temperature by around 10 degrees Celsius. The chamber must remove that heat immediately to maintain the programmed temperature. This capability is known as temperature compensation. Finally, airflow management is equally important. Too much airflow during temperature transitions may cause condensation on the battery surface. Too little airflow reduces temperature uniformity. That's why variable speed airflow control has become a standard requirement.
Let's finish with another topic that's often discussed. Battery reliability testing frequently specifies a temperature uniformity of plus or minus 0.5 degrees Celsius. Can half a degree really make that much difference? Can you quantify that with some real data?
The results are quite striking. We conducted comparative testing using battery cells from the same production batch. One group was tested in a chamber with plus or minus 0.5 degrees Celsius temperature uniformity. The other group was tested under plus or minus 2 degrees Celsius uniformity. Both groups completed 1,000 charge-discharge cycles at 45 degrees Celsius and 1C.
The results were striking.
The first group still retained 92 of its original capacity after 1,000 cycles. The second group dropped to 85% after only around 800 cycles. Post-test analysis revealed severe lithium plating on cells located near the cooler airflow, while cells exposed to warmer regions suffered accelerated separator aging.
In practical terms, a seemingly small 2 degrees Celsius temperature difference for an electric vehicle shortened battery life by approximately 200 charge-discharge cycles. That could represent the difference between roughly 30,000 kilometers and 50,000 kilometers of service life.
Exactly. That's why leading battery manufacturers now specify environmental chambers with temperature uniformity better than 1 degree Celsius, or even as tight as plus or minus 0.5 degrees Celsius, and temperature fluctuation no greater than plus or minus 0.3 degrees Celsius.
These specifications aren't about pushing technical limits for their own sake. They're about ensuring that engineers can accurately detect the battery's true degradation.
An environmental chamber for battery testing is much more than just a large refrigerator. From voltage signals that change within milliseconds instead of having those signals masked by temperature variations. So what advice would you give engineers purchasing an environmental chamber for synchronized battery testing? If I were buying an environmental chamber for synchronized charge-discharge testing, what would be the top things I should look for?
I'd recommend focusing on 3 key areas. First, communication capability. The chamber should support Ethernet communication, provide open protocols, and integrate directly with the battery cycler. Second, airflow design. Choose the airflow configuration that best matches your battery layout to eliminate temperature dead zones under full load conditions. Third, intelligent control logic. The chamber should actively output signals confirming temperature achievement and stabilization, rather than relying entirely on commands from the supervisory computer.
In short, an environmental chamber shouldn't simply heat and cool. It should also communicate, coordinate, and think as part of the entire testing system.
A perfect summary.
Thank you, Mr. Wang, for sharing your expertise today. From the survival of a single battery cell to the performance of an entire testing system, every tenth of a degree Celsius of precision reflects the industry's commitment to safety, reliability, and quality. Thank you for watching. We'll see you next time. Goodbye.